Hi, welcome back, everyone. This is Pre-Calculus Honors, section 14.2a and b, corresponds to section 11.1 or 11.2 in the notes packet. We're going to be dealing with permutations with repetition and circular permutations. All right, so our first objective for today is to solve problems using linear permutations that have repetition in them. Take, for example, that word grease. It has 3 E's in it. If we think about the distinct permutations, we have to think for a minute and say, wait, the E's are all the same, so how could we tell if something was different? Well, that needs to be taken into account when we talk about permutations, which are arrangements of objects in any order. So if we take this and we were just to do it like we did in the last lesson, we could do our lines with 1, 2, 3, 4, 5, and the 6th one there. We could put 6 letters on the first blank. We could put 5, then 4, then 3, then 2, then 1, which you know could be simplified down into 6 factorial. But wait a minute, we have a problem. It's because the E's are the same, and how could you differentiate one from another? Well, what we have to do is we have to account for that by dividing. So what we would end up doing is taking 6 factorial and dividing it by the 3 E's with a setup of 3 factorial, which if we did this in the longhand form, we'd have 6 times 5 times 4 times 3 factorial over 3 factorial, which we could then cancel out those and leave us with a total of 6 times 5 times 4, which is 30 times 4 for a grand total of 120. Okay? All right, so permutations with repetitions can be set up with this formula where you take n factorial and you divide it by all of the repeated letters you see and the number of repeats there are of that letter. Okay, that's the p factorial and the q factorial. So let's take another one. Let's take example 1 here. The word repetition. How many ways can we arrange these letters? Well, first, we've got to count how many letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 letters in the word repetition for 10 factorial. If there were no repeated letters, we'd be done. However, we have repeated letters. And you can see if we even started from the beginning, there's only one R. You don't need to worry about it. However, if we take a look at the E, see 2 of them, so 2 factorial, I'm going to notate that right below there, that's for the E. There's 1. I could write it as 1 factorial, but there's no need because 1 factorial is 1. Next up, I see 2 T's. So 2 factorial, notating that for the T's. Then I see 2 I's, 2 factorial representing the I's, which gives us our number of arrangements. Now, at this point, we could write it out all the way, or we could go ahead and multiply it out. Either way does not make a difference, but if we do this, 10 factorial is going to be over 8, because we know 2 factorial and 2 factorial and 2 factorial are all 2 times 1, 2 times 1, and 2 times 1, and 2 times 2 times 2 is 8. And notice I did not write the factorial symbol. And now when you use your calculator, you will come up with a grand total of 453,600 different arrangements of the letters in the word repetition. All right. Let's flip that over to the back side. Now, what if we start to put stuff in a circular format? Well, some ideas behind that will be with tables and people sitting around tables. Bracelets with charms on them, necklaces, all of those types of things are what we're talking about here. So we're going to solve circular permutations, some of which can be flipped over, some of which cannot, and that's what the term right here, reflective, is talking about. This is a flipped over. Okay. Suppose n objects are arranged in a circle. Examples, tables and bracelets. They can be done using this formula, n factorial divided by n, or n minus 1 factorial. Those are equivalent actions. I like to think about it this way. When you take n factorial divided by n is the number of places there are. And I'm going to show you when we do this next problem how we're going to work this out. 5 people sitting around a circular table. Well, we can apply the formula straight away. 5 factorial over 5, which we know is going to be 5 times 4 times 3 times 2 times 1 over 5. 5's cancel out, and we're left with 4 times 3 times 2 for a grand total of 24. Okay, one way to do it. Not my favorite method. I like diagrams or pictures. So what I like to do is draw a circle and put all of the places that these things, people, in this case, can be around the circle. And I just randomly picked those at any place. Now, what you would want to do here, using the line method like we've done in the previous lesson, put the 5 on any one of the lines. It doesn't matter which line, just put them on there. So let's start right here. And then let's go in a pattern around the circle with 4, 3, 2, and 1. And you can see that we're going to have 5 factorial. However, you can start anywhere you want. That's why we would take 5 times 4 times 3 times 2 times 1 and divide it by 5, because you could have started placing that 5 in any one of the 5 spots, in which you would still see the same pattern, producing the same exact value from above. You're going to see some problems in the homework that use circles. I recommend you write them out in this fashion. I think it really helps out. All right, next. We sometimes have a point of reference, such as the people are seated on the table next to a door, next to a window, or this is person number 1. When that's the case, we're going to take the circle apart and treat it as if it's linear. And then sometimes, depending if it's a bracelet or a necklace or a keychain, we might flip it over because you could see the same pattern front and back, upside down, backwards, but you're not allowed to flip over people. They sit at the table on chairs. All right, so let's take a look at these 2 examples here. Since a bracelet can be flipped over, it's reflective and therefore would have half as many permutations because the order will repeat itself when you flip it over. So, example 2. How many ways can 4 charms be arranged on a bracelet that has no clasp? This is one continuous pattern of this bracelet. There is no point of reference, and that's what the no clasp is getting at here. Okay, no clasp. So, no reference points. So, with that being the case, let's draw our circle over here. 1, 2, 3, 4 to represent the charms. Let's start by placing the 4 somewhere. Oh, here looks good. 3, 2, and 1. Okay, which then is going to give us 4 factorial. But don't forget we have to divide by the number of starting places, which will then produce for us 4 times 3 times 2 times 1 over 4. Canceling out the 4s, and give us 6 different arrangements. However, because it's a bracelet and we can flip it over, at this point we would then divide it by 2, which would give us a grand total of 3 different arrangements. Okay? How does that compare to example 3? Well, example 3, how many ways can 4 charms be arranged on a bracelet that has a clasp? Since it has a clasp over here, okay, this is a reference point. So we're going to treat it as linear. Treat as linear. So what I'm going to do in this problem is I'm going to go ahead and draw 1, 2, 3, 4 lines straight away. Since here's my reference point right over here, this is the clasp. And I'm going to write the 4, 3, 2, and 1 on the lines with the multiplication between them, giving us a total of 24. But don't forget, this is something small. This can be flipped over, so we're going to divide it by 2, and we're going to get a grand total of 12 different arrangements. Now, when you're doing these problems, you have to give them a try. You're going to make some mistakes. You're going to ask some questions. That's totally understandable. That's where you want to be with this type of lesson. And don't forget, in the notes packet and the worksheets, there are some examples in there also. And you can always go to Google and pull up any of these videos. Ask any one of the teachers, myself, Mr. Fossey, Mr. Sacco, for any questions. These are good questions to discuss. All right? So thanks again, and we will be talking to you soon.